products of exponential generating functions. Just as we have seen for ordinary generating functions, the product of the two exponential generating functions has a very natural combinatorial meaning. Lemma 8.20, let AI braces and BK braces be two sequences, and let A of x equals to the summations of AI times x to the I divided by I factorial, summing for all I which is greater than or equals to 0, and the B of x is equals to the summations of bk times x to the k divided by k factorial, summing for all k which is greater than or equals to 0, be their exponential generating functions. Define as Cn equals to the summations of n choose I times ai times bn minus I, summing with I starting from 0 to n, and let C of x be the exponential generating function of the sequence Cn braces. Then A of x times B of x is equals to C of x. In other words, the coefficient of x to the n divided by n factorial in A of x times B of x is Cn, which is equals to the summations of n choose I times ai times bn minus I, summing with index I starting from 0 to n. Proof. Just as in the proof of lemma 8.4, multiplying A of x by B of x involves multiplying each term of A of x by each term of V of x. The general term in this product is of the form x to the I over I factorial times x to the j over j factorial, which is equals to x to the I plus j divided by I factorial times j factorial times I plus j factorial divided by I plus j factorial, which is equals to x to the I plus j divided by I plus j factorial times I plus j choose I. Such a product is of degree n if and only if I plus j is equals to n, and the statement follows. Theorem 8.21, product formula for exponential generating functions. Let An be the number of ways to build a certain structure on an n-element set, and let Bn be the number of ways to build another structure on an n-element set. Let Cn be the number of ways to separate n braces into the disjoint subsets S and T, such that S union T is equals to n braces, then to build a structure of the first kind on S, and a structure of the second kind on T. Let A of x, B of x, and C of x be the respective exponential generating functions of the sequences An braces, Bn braces, and Cn braces. Then A of x times B of x is equals to C of x. Note that while Theorem 8.5 and 8.21, the product formula for exponential generating functions, sound very similar, they apply in different circumstances. Theorem 8.5 applies when n braces is split into two parts so that one part is I braces, that is, n braces is split into intervals. Theorem 8.21 applies when n braces is split into two parts with no restrictions. In other words, the first theorem applies when our objects are linearly ordered like days in a calendar or people in a line, and we cut that linear order somewhere to get two subsets. The second theorem applies when we are free to choose our two subsets. That is, they do not have to be consecutive objects in a line. Proof of Theorem 8.21. If S has I elements, then there are n choose I ways to choose the elements of S. Then there are ai ways to build a structure of the first kind on S, and bn minus I ways to build a structure of the second kind on T. And this is true for all I, as long as I is between 0 and n. Therefore, Cn is equals to the summations of n choose I times ai times bn minus I, summing with index I starting from 0 to n, and our claim follows from lemma 8.20. Example 8.22. A football coach has n players to work with at today's practice. First, he splits them into two groups and asks the members of each group to form a line. Then he asks each member of the first group to take on an orange shirt, or a white shirt, or a blue shirt. Members of the other group keep their red shirt. In how many different ways can all this happen? Solution. Assume the coach selects k people to form the first group. Let ak be the number of ways these k people can take on an orange or white or blue shirt and then form a line. Then ak is equals to k factorial times 3 to the k. So the exponential generating function of the sequence ak braces is a of x, which is equal to the summations of k factorial times 3 to the k times x to the k divided by k factorial, summing for all k which is greater than or equals to 0. Then the summation is equals to 1 over 1 minus 3x. Similarly, assume there are n people in the second group. Let bm be the number of ways these n people can form a line. Then bm is equal to m factorial, and the exponential generating function of the sequence bm braces is b of x equals to the summations of m factorial times x to the m divided by m factorial, summing for all m which is greater than or equals to 0, which is equals to 1 over 1 minus x. Let Cn be the number of ways the players can follow the instructions of the coach, and let c of x be the exponential generating function of the sequence Cn braces. Then the product formula implies that c of x is equals to a of x times b of x, which is equals to 1 over 1 minus 3x times 1 over 1 minus x. As 1 over 1 minus 3x is equals to the summations of 3 to the k times x to the k, summing for all k starting from equals to 0. And 1 over 1 minus x is equals to the summations of x to the n starting from, summing for all m starting from 0. It follows that the coefficient of x to the n over n factorial in c of x is Cn, which is equals to n factorial times 3 to the n plus 1 minus 1, then divided by 2. A particularly useful property of exponential generating functions is that their derivatives are very easy to describe. Indeed, x to the n plus 1 over n plus 1 factorial, the derivative of such a term is equals to x to the n over n factorial, and therefore the summations of a n times x to the n divided by n factorial, summing for all n which is greater than or equals to 0. If we take the derivative of such a summation, that will be equals to the summations of a n plus 1 times x to the n divided by n factorial, summing for all n which is greater than or equals to 0. Note that the constant a n has been shifted after to a n plus 1 for the same term after the derivative. The following example makes good use of this observation. Example 8.23. Let b of x be the exponential generating function of the Bell numbers b of n. Prove that b of x is equals to e to the x minus 1. Solution. We know that b of n plus 1, the n plus 1th Bell number, is equals to the summations of b of I times n choose I, summing with I starting from 0 to n, if n is greater than or equals to 0, and the b of 0 is equals to 1. Multiply both sides by x to the n over n factorial, and the sum over all n which is greater than or equals to 0 to get that the summations of b of n plus 1 times x to the n over n factorial summing for all n which is greater than or equals to 0, which is equals to double summation with outer summation summing for all n which is greater than or equals to 0, with inner summation summing for all I starting from 0 to n, with the term b of I, the real number, times n choose I times x to the n divided by n factorial. Now note that the left-hand side is a b prime of x, while the right-hand side is b of x times e to the x by lemma 8.20. Therefore, we get that the b prime of x is equals to b of x times e to the x, and the b prime of x divided by b of x is equals to e to the x. And if we take the integral, ln of b of x is equals to e to the x plus c. So if we're setting x equals to 0, the left-hand side is ln 1 equals to 0. Therefore, we must choose c equals to minus 1 on the right-hand side. Therefore, ln of b of x, the ln of the real number of x is equals to e to the x minus 1. And if we take out the ln, we know that b of x is equals to e to the x minus 1. Note that the minus 1 is in the exponent of the first e, as claimed.